In the previous video for section 15.3, we calculated the work along those three different paths. I'd like to begin by showing you an alternate way of calculating the work for the second path, where you're moving along the curve x equals y squared. You can let x equals t, then y would have to be the square root of t for the time interval from 0 to 1. So that dr, the path, is ti plus the square root of tj. When you take the derivative of t, you get 1, and the derivative of square root of t, using that power rule, you get 1 over 2 square root of t. And then when you replace the x and the y in the vector field with x equals t and y equals square root of t, we get the following vector field in terms of t. When you calculate the line integral for work by taking f dot t, when you multiply those corresponding components and add them together, you get the following definite integral from 0 to 1 of 5/8 t to the 3/2 dt. So we end up with a different final integral, but when we calculate the work, we get 1/4. So again, we've calculated the work along three different paths in the same vector field with the same start and the same endpoint. That happens when you have a conservative vector field. And we want to verify that the vector field is conservative. Our original vector field, again, is 1/2 xyi plus 1/4 x squared j. If you take the partial of n with respect to x, that's going to be 1/2 x, and the partial of m with respect to y, you get 1/2 x again. If those two partials are equal, then we can say the vector field is conservative. And if it is conservative, then there is a potential function. And the way you find the potential function is integrating m with respect to x and n with respect to y, and you'll find that the potential function is 1/4 x squared y, and I would also put a plus c there. It is actually not necessarily when we use the fundamental theorem of line integrals gives us an alternate way of evaluating the line integral. In fact, you don't need to even use the f dot dr. What you do is you find the potential function and evaluate the potential function at the end point and at the start point and subtract. The line integral is that difference. This is called the fundamental theorem of line integrals, where you can calculate the work by finding the potential function, evaluate the potential function at the endpoint, which was located at 1, 1, evaluate the potential function at the start point, which was located at 0, 0, and subtract, and you will see that this is 1/4. So in this case, we're not even using a path, we're using the potential function. And you can only use this technique when the vector field is conservative. So this was illustrated here, the fundamental theorem of line integrals. Suppose you have this path represented by r of t, and you have a vector field f if it's conservative. If it's conservative, then the line integral for work can be evaluated by the use of a potential function, where you're evaluating the potential function at the end point, the potential function at the beginning point, subtracting. This is your fundamental theorem of line integrals. That could save you a lot of time in future examples when your path may be quite complicated. Rather than go along these varied paths, you can find the potential function. If this is a vector field in space, then you would find the potential function. It would be a function of x, y, and z. Again, you would evaluate the potential function at the end point and at the starting point and subtract. In this example, we want to use that fundamental theorem of line integrals to calculate the work where c is some curve beginning at the point -1, 4, curving around, ending at the point 1, 2. Moving along this vector field, moving through that vector field. If this vector field is conservative, then we can use the fundamental theorem of line integrals. If we take the partial derivative of the n with respect to x, that's 2x, and m with respect to y is also 2x. So that's a test, do a quick test to make sure it's conservative. And then you want to find the antiderivative of m with respect to x and n with respect to y to find that potential function. You can go back to the previous section to review that, but you're integrating 2xy and you're integrating x squared minus y. Integrating 2xy with respect to x, you get x squared y plus some constant that could have y's in it. And when you take the antiderivative of x squared minus y with respect to y, you're going to get x squared y minus 1/2 y squared plus some constant with x's. So when you calculate the antiderivatives, combine those to find the potential function. The potential function is x squared y minus y squared over 2 plus some constant. You want to evaluate that potential function at the endpoint, which was 1, 2, located at the coordinates 1, 2, and then evaluate the potential function at the start point, located at negative 1, 4. Plug those into your potential function here and simplify, you get the value 4. So that gives you an alternate way of finding the line integral for work, because in a conservative vector field, it really doesn't matter what path you take. You can use this fundamental theorem of line integrals to find the value of work. This theorem is about the independence of path in conservative vector fields. If that vector field is continuous, then the line integral of f dot dr, that's your line integral for work, is independent of path if and only if f is conservative. So that means it doesn't matter what path you take. If the vector field is conservative, the work is going to be the same no matter what path. It's independent of the path. If the vector field is not conservative, then it does depend on the path, and you would have to evaluate the line integral, coming up with the parametrization for the path. If it is conservative, it's independent, doesn't matter what path. So I would either select the easiest path or use the fundamental theorem of line integrals. In this example, we want to find the work for the force field given by this function of 3 variables equals e to the x cosine yi minus e to the x sine yj plus 2k. We want to show that this line integral is independent of the path. In other words, we want to make sure that this is conservative, and then calculate the work done on the object moving along a curve, beginning at the location 0, pi over 2, 1, ending at the point 1, pi 3. So you want to first check that the vector field is conservative. And to check if a vector field in space is conservative, you can calculate the curl. Find those partial derivatives. If the curl is equal to 0, then we can say the vector field is conservative. Here we have identified the components of the vector field in space using m, n, and p. And the partial of p with respect to y equals the partial of n with respect to z. The partial of p with respect to x equals the partial of m with respect to z. And the partial of n with respect to x is equal to the partial of m with respect to y. So the curl is equal to 0, and we can say that the vector field is conservative. So we want to find the potential function. The way you find the potential function is you integrate m with respect to x, n with respect to y, and p with respect to z. And you will get that the antiderivative, that potential function. These are your m, n, and p, and we want to integrate that. If you integrate m with respect to x, you get e to the x cosine y plus g, which is a function of constants or y's and z's. When you integrate with respect to x, you're going to treat y and z as constants. Okay, you integrate the n with respect to y, treating y as the variable and x as a constant. The antiderivative of that is e to the x cosine y plus some function of constants that includes x and z. You're treating x and z as constants. When you integrate the p with respect to z, the antiderivative of 2dz is 2z plus some constant that could have x's and y's in it. So the potential function is found by taking what they have in common, that e to the x cosine y, and this 2z. This doesn't appear in the first two antiderivatives because in those cases we treated z as a constant. And again, the e to the x cosine y doesn't appear in the last integral because in the last integral we treat x and y as constants. So that's why we're including these function of the variables that we considered constants. So we find that the potential function, comparing these three versions, we can conclude that the potential function is e to the x cosine y plus 2z plus some other constant. Now to calculate the work done on any curve, since the vector field is conservative, you can evaluate the potential function at the endpoint and at the start point. So we're evaluating that potential function at the ending point and the starting point and subtracting to get the work is 4 minus e. Okay, in this example, we want to evaluate a line integral. We want to evaluate the line integral for f dot dr, where f is this vector field y cubed plus 1i plus 3xy squared plus 1j. And we've got these path, which is starting at 0, 0, moving to the point 2, 0, or moving along the path from 0, 0, the straight path. And there's different options for solving this. We can evaluate the line integral using this parametrization. Or if we test to see if this is conservative, we can evaluate the potential function at the end and start points. Or if the f is conservative, we can take a different path. Now consider each of those options, try out which one you think is going to work, and then move on to the next video to see these options worked out.